Recording's rolling. It's Monday, January 5th, 2026. Welcome back from the break. I hope you guys had a good break. Here's top scientist for the midterm. So awesome job. He made a top scientist list. All right. So the day before we went to the break, I got an email from a teacher at Ralph Williams Elementary. Here you go, Ralph Williams Elementary. So they're hosting a STEAM night on Thursday, January 15th. This elementary school is just across I-95. I uploaded a link to Google Classroom that shows a map exactly where it is. It's actually not too far from here. Right? So Thursday, January 15th. And the teacher is looking for maybe like physics or science demos or like what would high school science class look like. And it'd be really helpful to have student volunteers for this. So I came up with a list of demos that I could do. A lot of these are like labs or demos that you guys understand in class. Some of these are new. Like here, for example, one that we haven't even done yet, and there's quite a few of these are like Stirling engine. If you put a cup of hot water under this, then it'll spin and turn into mechanical energy. Do you guys remember? You guys remember roller drop? Remember pairing it with a friend and you drop a roller, and based on how far it falls, you can determine your reaction time. You guys remember doing that way back in the day? Like, so if you see something like, yeah, there's some pretty cool things from this class. Here's a whole list of things that maybe I want to be able to communicate to 8 or 9 year olds, over at the elementary school. Then here's what I do. I'm going to pass around the sign-up sheet. So just write your name. And if there's particular demos that we would be interested in presenting, right? And I've got a whole list here. Like here that you guys see that mechanical advantage pulley system over there. Maybe I could cart that over somehow. Right? Then mark down the numbers, and then I could have an idea too of what you might be interested in talking to little kids about. So I'm going to pass this list around. Okay, I actually got a few names on it. Pass this around. Again, if you're interested in volunteering on Thursday, January 15th, this would be from 5 to 7 p.m. over at the elementary school. Just write your name on there, and then I can send an email later today and say how much interest or how many students might show up. Right? All right, so next thing, there's a Jamaica Hurricane Disaster Relief Drive going on until January 16th. I'm just gonna put a box down by my door, probably for the next week or so. Right, I threw some things in the box already just to get it kind of started. But if you want to bring anything in, I could go to Jamaica and help them out. So they're recommending non-perishable food, clothes, toilet sheets, hygiene products, first aid, the kind of things, right? And so that box will be in my room for about a week, and then I'll just take that to the office. You can have it there. All right. For my AP class specifically, I have opened units 5 and 6 on AP Classroom. Right, so those look like these. Right, so AP used to teach us all in one unit. They broke this up into two because there's kind of a lot going on there. Right, so I have tentative due dates here. Was it the 12th and 13th? Right, I might end up bumping this back a little bit, but that's just for my AP class. Right, so got that there. Uh, so what formulas we're looking at on this AP page? I want to update you guys with this. Okay, so got a little bit of recap already because we've done some rotational pneumatic already. Do you guys remember turntables? Turntables. Okay. So I got this turntable here. Here, what if I stack some items here? Right, give this a spin. Right, guys. Do all these objects right now have the same turns per time? Yeah, that's called angular velocity. They all have the same angular velocity, right? But what if I put a speed gate here and this goes through speed gate and this goes through, right? Those be different linear speeds. Yeah, it could be like a tangential velocity sometimes called, right? And the connection between those different kind of velocities is right here. So here's the turntable turning in radians per second, angular velocity, right? But the linear velocity picked up on speed gate, right? Right. You have to multiply by your distance from the center, r. And that'd be different, right? Now, there's also how far, how fast, and also acceleration version. Now, those are, whoops, not that one yet. Right, those are here, here, and here. Right, so they put the velocity and acceleration up here, and for some reason they put the displacement one way down here. I don't know why, but these three kind of go together. Right. There's also, do you guys also remember kinematic formulas? Now, the linear version went like this. Right, so how far, how fast. Right, we got time, got acceleration. Right. But then on a turntable, the whole turntable turning, right? Here's how far it could turn, say, in radians. Here's how fast in radians per second. Something like that, right? So there's kinematic versus this. Now those formulas are the top three right here. So those right there, right? But what about this whole gap right here? What about these 9 guys? So these are all related to rotational dynamics, and I'm going to start talking about these today. It's going to take me at least a couple of days to go through these. Okay. And by AP's book, it breaks it up into unit 5 and unit 6. So I'm going to I'm going to section off these top 4 right here. Okay. And then these bottom 5 right here. Okay. So these top 4 right here, I'm going to call these unit 5. Again, this is by AP's book, and call these unit 6. So when my AP students are getting into AP classrooms, okay, here's unit 5, here's unit 6. Right. Unit 5 also includes this kinematic stuff, which you guys saw a little bit after. Okay. But collectively, all these together, these 9 right here, are rotational dynamics. Okay. All right, so we'll take it's sort of like forces, but at some radial arm, maybe causes things to rotate, right? And these are all related to that idea, right? Right, and that's a lot of what you guys are going to see today. Right, any questions so far? All right, guys, right? All right, so let's break out these posters here. Posters. Okay, start checking through these. Okay. Now the first 2 posters are going to be review, like here, like you guys saw this one last semester. You guys saw this last semester. We did a little review, right? And then I have a few trivia, and then it'll get to the like meat of this topic. Okay. Here's a little bit of a review. I just want to remind you guys that there are different kinds of acceleration. I have 3 different kinds of acceleration we're juggling. Right? They have different units, different concepts. The first kind you learn might be called tangential acceleration. It's just acceleration in a straight line. So are you speeding up or slowing down in a straight line? Okay. You guys learned for a turntable, the whole turntable could speed up or slow down its rotation. Maybe it spins faster, 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 or you take your finger off and friction slows it to a stop. That's some kind of angular acceleration. If it's changing how fast that's rotating. Okay. Right. So tangential acceleration can be in meters per second squared. Angular acceleration is in radians per second squared. But these can be related to each other because you could very simply, depending on which way you're going, either divide or multiply by your distance from the center. And if you know one, you can know the other. Okay. Also, what force is holding something in a circle? Is that called centripetal force? Right? And maybe if you had an object on a turntable, it could be provided by friction, but there's some friction force. Otherwise, these would go flying, or they wouldn't move in a circle. Okay? So that friction force actually is centripetal force. Well, if you divide by the mass of the object, you get centripetal acceleration. Guess remember that could be v squared over r, or omega squared times r. Ooh, guess what? All right, so that's all review. So we're doing review there. Okay. All right, next we got. Okay, there's turntable slows to a stop. We got distance, velocity, and acceleration graphs, but these are all angular type, right? So slowing to a stop is velocity goes to 0, so on. Okay. All right, I got variables and corresponding units. Okay, now the top half of this about you guys have seen already. Angular displacement could be in radians. Okay, angular velocity in radians per second, and so on. Okay, but the bottom half of this is going to be new stuff. Right, so here's where we're going to be breaking new ground. Right, you guys see this capital I? So in physics, this is going to stand for moment of inertia or rotational inertia. It has to do with what's the inertia of a rotating system. Okay? So you remember how in a linear system, mass represented inertia, right? So if I have different masses and I put the same force on both of these, this little one go flying across the room. This big one, it hardly accelerates at all. The larger the mass, the less the acceleration. That was Newton's second law, right? Now, interestingly, in a rotational sense, it's not just how massive is something, but it's how that mass is distributed, which you guys are going to see later today. You guys see this unit right here? It's not just kilograms. It's kilograms times meters squared. So something about the distance located, right? Something about that. So like this turntable right here has some thickness to it, right? Has some mass, right? Here, I just flip the screen. We flip that back. Okay, we're back. Okay. Do you think I feel some inertia trying to get it to speed up from rest, right? And then maybe once it's spinning, it's kind of hard to bring to a stop too. Right? You guys ever ride a bicycle that has huge wheels on it? Like a lot of bicycle wheels have like 24 or 26-inch tires, but there's some that have like 27.5-inch tires. Right? It's kind of hard to pedal to get them going, but once it's going, it's also hard to stop a bicycle too. Right? Right, so the different rotational inertia. Right? Torque, you guys gonna see this Greek letter tau. This is like using a wrench to turn a nut or opening a door on its hinges. Right? So I have posters for this, but you guys see this later. Okay? So it's kind of like a force. I see newtons to represent a force, but also times meters. So it's the location of that force you guys are going to see. And you have some labs lined up later this week where you guys get to work with torque. Okay? Right. And then these bottom 2, okay, now these get more abstract. You guys see this capital L, angular momentum. So say like if I spin a coin here, guys, how can I get this coin to stay on its side if I try to prop it up? Isn't that like nearly impossible? Nearly impossible. Spin it. Ah, I heard that. Here, spin it. Whoops. What's this? You guys see if I give it a spin? Oh, that'll stay outside. Because this property right here, angular momentum, wants to be conserved. So once it's spinning, it wants to maintain its orientation. Kind of like regular linear momentum also is conserved during collisions. You guys remember that? Right? I have a whole bicycle wheel demo, which I won't quite get to today, but that's what I got this for. So eventually I'm going to get this a spin, sometime later this week, and do some crazy things with the bicycle power. Right? All right. All right. So that's a quick rundown. Here's a little bit different way of looking at this. So I have rotational analog. So what was going on in linear motion? What's the rotational equivalent? So time is still time. I've got displacement, velocity, acceleration, but you guys saw those last semester. Right? Right. So taking the place of mass is now going to be rotational inertia. Oh, and I'm starting to tell you kind of what it is right here. It's mass times location squared. Hold on to that idea. Right? You guys see later what this is. You need to feel it later in class too. Right? Oh, look at it. Look here. It's Newton's second law of motion. F equals ma. So a net force results in mass accelerating. Now, the rotational equivalent is called torque. Right? So if I apply a force at some radial arm distance, look at that R cross F right there. Okay? It's like, here, we'll do a little demo for you guys right here. I'm going to open this door. You guys see I'm walking over to this door? Okay. Here, guys, why is the door handle opposite of the hinges? Why not put the handle right next to the hinges? If I did that, it would be really hard and really easy to open the door. Really hard. I could push really hard and the door would hardly open up. Go ahead and put the handle in the middle. Yeah, a little easier there, but if I put it all the way on the opposite of the hinges, little tiny force opens the door, no problem. Huh. Well, why is that? It's interesting. That's what this is saying right here. So I can take this force, but if this R represents the width of the door. You guys see that? Right? And push and get that torque, that turning moment, and that'll open the door. Okay? Actually, it'll cause that door to undergo an angular acceleration. That's what that alpha is while I'm pushing it, right? And that I has to do with, something to do with the rotational inertia of the door. Like how massive is the door, sort of, right? But more on that later, right? Here's, okay, and then by AP's book, this whole top section is in Unit 5, but these bottom two lines are, well, AP puts it in Unit 6, started recently, right? We got momentum is mass times velocity, and here's the rotational equivalent. Right? This is capital L, so I'm doing that's spinning coin or that bike tire I'm eventually working towards. Right? But do you guys see how this I takes the place of this M, and this omega takes the place of this V? Is that right? So there's the symmetry all over the place in physics, where yeah, if you just pop in the rotational equivalent for a linear value, a lot of times you get a perfectly valid formula like you're seeing right here, right? And then also same thing with Newton's second law, F equals ma, tau equals I alpha, sort of equivalent. Right? And then there's energy. So you guys remember in linear motion, kinetic energy, 1/2 mv squared, right? Well, if you get something that's rolling across a plane or maybe down an incline, right? Got different rolling objects right here. Some energy can show routes into making something roll or rotate. And you can quantify that exactly as this, 1/2 I omega squared. Right? If I know what's the rotational inertia of this ball, or what's the rotational inertia of this cylinder, that might take the place of this I. And if I get it to roll, maybe I can quantify that omega. And then how much energy did that take? That's what that K is. Okay. Quick rundowns right there. So quick what to look for. Right now, the next few posters are all kind of lead-ins or review or a little bit trivia. Okay? So do you guys remember center mass that I did just last semester with you guys? It's just a weighted average of mass. So if I had a big mass and a little mass and I stick a stick through them, just like that. Okay. Now I balance this on my finger. Probably balance closer to the large mass, but where exactly? How can you quantify that? The way you do that is you do mass times location plus mass times location divided by the sum of masses. It gives you the average location. Right? Now this is with 2 masses, but if you had like 10 masses or 20 masses or 100 masses, you could use the sum of mass times location divided by sum of masses gives you the average location called center mass. I have a center mass lab for you guys eventually too. So next couple weeks for that. Okay. Okay. Here's a little extra. I don't know if it's going to show up in this class or not. Maybe it's good to know. Why not? What makes something stable or unstable according to physics? Right? Like here, if I set this object right here, no way is that going to fall. I could leave the room, come back 10 years from now. It's just still just sitting there upright, no problem. Right? But what if I try to balance this pen right here? Try to balance this pen. Is it easy or hard to balance this pen? Yeah, it's nearly impossible, isn't it? Nearly impossible, right? So why would this pen be unstable, like right here, versus this object just sitting here would be more like this, which is fit, right? So the physics definition goes like this. If there's any small deviation, right, but there's little rumblings in this tabletop, or maybe the air currents are floating around as the air conditioning is kicking on, or I'm talking for that matter, right? Little vibrations, okay? And the center mass is going to jiggle around tiny, tiny. You can't even detect it with your eyes. Okay? But if it just wants to return to its original position, like this object here, or if you have a picture hanging on the wall, it's scoot a little bit, it just goes back to the original. Okay? That would make it stable. Okay? If what about a ball on the floor? I mean, if I give this ball a push, right, then it ends up looking kind of like it started, so we'll call it neutral, right? But over here, say if I'm trying to balance my pencil or pen, right, or if you put a ball right at the top of a hill, right, which way does it roll? Well, it's going to roll something. Right? See, any small deviation in its motion, any small displacement, it's just going to further accelerate in that direction. So that's what makes something unstable. Yeah. And there's extensions from this too. So, like if you look at a big old cruise liner, it's scooting around on the Atlantic Ocean, right? How does it stay afloat? Or what if there's a big ocean wave that tries to knock it over? How could that stay upright? Right? That branch off in there. Right? Right. Yeah. Here's another bonus poster I have for you guys. Bonus. So maybe after school today, if you guys get your phones out, here's a really weird trick. Now this one gets really deep. I'm not gonna fully explain this, but at least I'll present the idea to you. Okay? Uh, is that if you there's certain axes of rotation that are stable or not stable. Okay? So if I spin this around this axis, that could just spin around like that. If I was up in space and gave this a spin, it would just keep spinning like that, no problem. Right? Or around about this long axis, right? No problem too. Right? That can just spin like that. If I was up in space and I do this, it'll just right. But interestingly, on this intermediate axis, there's this intermediate axis theorem. If I try to spin it like this, it's nearly impossible to make one clean flip like that. It always wants to do like some like weird like rotation like that. Right? You can try this too. Right? It have kind of a small space right here to do this, but it's nearly impossible to do this. Right? And up in space, if I gave this a spin like this, it might start to spin like that, but then it would just like randomly flip and go like it's a really weird aspect of corner physics. If you set up a O'Neill cylinder like this would be stable. But if it's like long like this, trying to rotate along this long axis, this would not be stable, and it would eventually just go the wrong way. Yeah, if you want a better explanation for this, there's a Veritasium video where he talks about like why these are unstable, but these would be stable. Okay, that gets pretty deep. Right? But again, that's just kind of bonus for you guys, kind of food for thought. All right, but here's back to the main part of this class. So what is inertia in a rotating sense? And this is one that you guys are about to get your hands on and feel for yourselves, because I have these right here. This left picture, you guys see I got a meter stick with a couple masses. Boom, there it is. Meter stick, couple masses right there. And this right picture, okay, also same meter stick with, okay, so maybe same masses, right? Here's meter stick. Oh, this mass is way out on this end. And then, oh, this mass way out on this end. Right, so you guys see that these two are the same, except these two masses are scooched in and these are like on the far ends. Okay, now, what if I grab both of these? Okay, left hand, right hand. Okay. Guys, if I close my eyes and pick them up, do they feel identical?
Yeah.
Yeah, identical, same weight. What if I shake them back and forth linearly? Do they feel like the same mass? Yeah, same mass, same weight. Okay. But what if I start to shake them back and forth like in a rotating sense? Okay. One of these turns out very easy to do. One of these very, very hard. Which one's very easy to shake back and forth? The one on my left hand right here?
Yeah.
Well, okay, that's not too bad. That's pretty easy. Okay, but what about this one? Ugh, so hard. So hard to shake back and forth. This one, no problem. This one, so hard. Oh, this one has a lot more inertia. What? It's a lot harder to change its state of motion. Huh. Right. I'm going to pass these around so you guys get to feel that for yourselves too. Maybe I can follow the same as a volunteer page that's going around. Right. And what's the physics formula behind it? Well, it's right here. It's the sum of mass times location squared. Location from, I guess, the central pivot point in this case. Right? So if I'm ignoring the stick and just focusing on these masses, maybe that's like most of the mass. Okay. Here I got some mass times this distance r being squared. Plus there's one on the other side, mr squared. Isn't that like 2 mr squared? Is that? Okay. But on this picture on the right, I scooch these masses 3 times further away. Guys, if I throw a factor of 3 on this r, what does the inertia become? What's 3 squared? 9 times as much. So I got this 3r being squared, this 3r being squared. 99 is like 18. You guys see 18 mr squared? Right? Now if you compare this to this, what is 18 compared to 2? 9 times as much. You see it? All right. We're starting to get this. Okay. Now these are for point masses, like individual points. You can add up individual points, right? But a lot of really objects like this one's pretty close to a sphere. Is this like some solid, rigid object? So what if it's not a point mass that's rotating or about a central axis. What if it's like one of these other shapes? How do you do this? Okay. So this has been worked out. You can do this with calculus. It takes a little fancy calculus, but okay. And so let's start with the point mass and we'll work from there. So I got a point mass, say like revolving around the central axis. Notice that every single one of these is rotating around some defined axis. Okay? So that's just mr squared. Right? Oh, look at the ring. Guys, isn't the ring just every single point is equidistant from that central axis? So it's this mr squared. This, like if I break this ring into a billion parts, isn't every individual part just itself mr squared? So the aggregate effect is still mr squared. M is the mass, r is the radius. You guys see that? Right. But what about, okay, let's go all the way to the end. Guys, look at this basketball. You guys ever spin a basketball on your finger? I spin a basketball. Okay. Now it takes some effort to get it going. Looks like that basketball has some inertia. Huh. It's spinning, has some angular momentum. So how much inertia does that have? Well, if you break the basketball into a billion parts, isn't the basketball effectively like the surface of a spherical shell? Is that? And notice I have it rotating about the central axis. So some parts are maybe on that axis, maybe a couple points. Right? And then some points are the full radius of the basketball away, maybe all around this like equator. Right? And some parts are, well, yes, some percentage of it. So if you run mr squared for a billion points on a basketball surface and do the calculus, it turns out it's 2/3 mr squared. Okay. Now, I'm not going to have you guys memorize this table. You don't have to memorize any of these. I might have you guys apply some of these, but I would give these to you. And same thing on the AP exam. If AP wants you to apply some of these, they would provide you the formula. Actually, AP likes solid cylinders a lot. Solid cylinder works out to half mr squared. Okay. Ooh, let's go back to this coin. Guys, look, I got a thin coin rotating about its central axis. This right here. Now, as long as it's a pretty thin coin, the rotational inertia is approximately 1/4 of the mass times the radius of the point squared. Okay, it's pretty close. Okay? What if you have a stick that's rotating about its center? That's like this. What if it's rotating about its end? That's like this. Okay. Hey, I'll ask you guys. Guys, which do you think has more inertia? If I hold this at the center and go like this, or if I hold it at the end? It's like, ugh, which has more inertia? Yeah. If I hold it at the end. In fact, you can see exactly how much more right here. This is 1/3. This is 1/12. Ah, isn't 1/3 more than 1/12? It's about 4 times as much, isn't it? Yeah, yeah. And finally, here's the bowling ball or solid cylinder. Works out 2/5 mr squared. Right. So the general rule is this: if the mass is distributed closer to the center, that's a smaller rotational inertia. If it's spread out, it's a larger rotational inertia. See how the basketball has more than the bowling ball? I mean, mass inside. Like if these were equal masses somehow. Okay. Like 2/3 is more than 2/5. All right. Next one. Let's go a little deeper. So parallel axis theorem. If you notice that, remember how all the objects of this page are showed rotating about some defined axis for these red statements to be true, right? What if they're rotating about a different axis? For example, a ball rolling across the floor. You guys see this ball rolling across the floor? It's actually not rolling about its own center. It's rolling about this point down here at the bottom. You guys see that? Right? Like a car tire. At any instant, the bottom point on the car tire has an instantaneous speed of 0. Right? And if your car's going 60 miles an hour, the top of the wheel is going 120 miles an hour. It's going twice as fast as the car's going at any particular instant. Right? So what's actually going on here? So what you do is you say it's the rotational inertia of the actual rotational inertia, I right here, is equal to the table value. That's what I naught is. I naught is any of these 8 red values right here, right? Plus mass times the offset distance squared, right? And the idea of parallel axis is we're looking at this axis compared to this axis. And it would be parallel axes, right? So you take I naught straight off that table, you add this md squared, the offset distance, and it gives you the actual rotational inertia for, say, like this revolving object, right? And if you have something rolling across the floor like this, right, well, here I got a basketball. The table value says 2/3 mr squared. Right, that's this right here. But again, that's spinning on your finger, right, which is not rolling across the floor. They're rolling across the floor. Well, it turns out the offset distance is pretty much the radius of the basketball. So that's like mr squared, but this bit's like this bit. It's like the same idea. Right? So you can actually add these together and get the inertia associated with the ball rolling across the floor. Right? Like how much inertia does it take to push it to get it in motion or to stop it if it's rolling towards you? Right? That's actually this. A little bit. All right. Torque. All right. So here's I have a wrench trying to turn this nut, but You could also, in your mind, have the example of I'm trying to open a door. Right, and there's door hinges, and on the opposite side of the door is the door handle. I give the door handle a little push, and it opens the door. You guys see it's the same thing, right? If you're looking like straight down on the door, here's the hinges, here's the handle, right? So let's say it's a rusted over nut. It's really hard to turn. Right? Guys, where do I want to grip this wrench? Do I want to hold it here and try to push? Do I want to hold it back here, try to push? Yeah. How about over here? Okay. And here's the physics that tells you exactly why. Okay? Because you're able to take advantage of this full radial arm. Right? Okay, so it's like full width of the door, full width of the wrench here, right? Times however hard you push, right? That gives it a torque, right? Now, so I'm turning a moment. Now you can turn that nut. Guess that. Right. How about this? You guys see that cross right there? You guys see that cross?
Yeah.
Right. That's called a cross product. Now, it's a special kind of multiplication. You guys know how in a calculator, multiplication is normally commutative. Like if I multiply 3 times 8, that's 24. But what is 8 times 3? Is that also 24? Same thing, right? Right. But when you're working with vectors, then directions also matter. So the idea of cross product is that you only get to multiply the perpendicular components. Guys, what's the best way to push on the wrench? Should I push on the wrench straight towards the nut? No, that'll never turn the wrench. That gives me no torque at all. Right? What if I push exactly perpendicular? Is that really good? Actually, that's the best thing I could do, isn't it? Right? What if I push off on some angle? If I push off on some angle, isn't it only the perpendicular component that's actually doing anything? Yeah. Now, if I define the angle as the angle between the vectors, theta, like on this picture, then the torque is actually RF sine theta. And the sine theta tells you what happens with the cross product. Okay? Is that you guys remember last semester there was a dot product for work, and that was the parallel components. This is a cross product, also for vectors, but now it's perpendicular components that matter. Okay? Like that. Here's a little tricky thing. Guys, what if you're given the angle that's complementary? Like this, you guys see this angle right here? If you were given that angle, this would no longer be sine. It would now be what? Yeah, cosine. You guys see that too? Yeah. Is that right? Now, if you have a net torque, suppose I have some applied torque, and maybe I subtract out the torque from the rest over here at the point, so I get some net torque, some net effect. Okay. Then that can result in I times alpha. And this green box right here is Newton's second law applied to rotating systems. It's like F equals ma. Now it's tau equals I alpha. You see that? Okay. Where maybe this I could be the rotational inertia of the wrench. That looks a lot like this. Hey, does that look like your wrench right there? Looks like a wrench, at least in this context, right? And the alpha would be this like speeding up spinning in a rotational sense. Like, that's it. Use that way. Okay. All right. Okay, you guys good so far? All right. How about this? Guys, if I move this way, if I'm trying to loosen this nut, am I turning this clockwise or counterclockwise? Counterclockwise, right? Guess that? Right. Unless you change your perspective. Let's what if you just, what if you pick up the paper, you walk over down on the other side of the paper, like down under, and you look up this way. Okay, so I'm trying to loosen the nut this way. According to the person down here, this person says, I'm turning which way, clockwise or counterclockwise? Clockwise. So whether it's going counterclockwise or clockwise depends on where you're standing in the room. Right? Like if I had a transparent clock and you stood behind the clock, it would look like the clock was going in reverse. You get that? Right? So what I'm trying to build up to with that is that clockwise and counterclockwise is not very mathematically precise. There's a better way to describe this mathematically, but you have to think kind of abstractly. Right? So that's going to bring us to what's called the right-hand rule. Right? So I have to open up a z-axis so that everybody can agree on the direction of the torque regardless of where you're standing in the room. So here's how a torque works from the point of view of right-hand rule. If you point your fingers in the direction of, say, the radial arm or the width of the door or the axis of the wrench, right? And you curl your fingers in the direction of the force, or you can just do this with my middle finger, right? Then this has to be with your right hand. It's the right hand rule. Then your thumb will open up a third axis. See, I have like an X, Y, Z axis system. You guys see X, Y, Z axis system, right? And that torque you can describe as positive or negative rather than clockwise or counterclockwise. Right? Now, positive is usually considered counterclockwise and negative is clockwise by convention, right? But with this right-hand rule, you get all that for free. You just take positive and negative torque, right? So if I go over to this door again, okay? Here, guys, here's the hinges right here on the door, okay? So the width of the door, there's like the R. If I push, say, towards the hallway, that's like the F, right? Do you guys see which direction is the torque? Up or down? Up. According to right-hand rule. Yeah, so the torque would be up, right? And again, regardless of your frame of reference, it would always be up. No, nothing is actually moving up. Everything's just moving along this XY axis plane, or sorry, XY plane. Yeah.
How would the torque ever go down if you're always using your right hand? Would you ever flip it over?
Ah, yeah. You could totally flip it over. So if I go back to this wrench, suppose I want to tighten this nut. Right. So now I'm applying a force down this way. Right. Right. So here's my R, here's my F. Right. So go like this, and see now my thumb's pointing into the page. Is that
Okay.
yeah? And that would be a negative torque, which would look like clockwise from our point of view. That would be negative. Yeah. So clockwise is negative, or counterclockwise could be positive. Right. Yeah. There's nothing actually moving up or down. It's all constrained along this XY plane. Right. That's the way you can describe that. Right. Right. Okay. You guys ready to get real technical here? Okay. So, yeah, expand your imagination a little bit here. Let's take this into 3 dimensions. So, what if you have some? Oh, look at this. You guys see I, J, K? This basically stands for X, Y, and Z. So I have a 3 dimensional system here, like an X, Y, Z axis system. Right? And what if I have a nut here at the origin at 0, 0, 0, and I have the wrench at some crazy orientation? See, it's got like an X, Y, and Z way to describe the crazy orientation of this wrench. Right? I could also push on the end at any crazy direction I want to. And as long as I don't push parallel to the wrench, it's going to cause some kind of torque on this nut at the origin point, isn't it? Right? Now, how can you mathematically describe that? You can do that with this cross product using a matrix and actually taking the determinant. Right? Now, this goes even beyond anything AP is going to ask, but if you take physics in college or mechanical engineering in college, you're going to have to eventually do this. So I just want to plant the idea today so you can say, okay, kind of see where that would come from, but we're not actually going to solve any of these in class. Right? What I will do later today is I will upload this video to Google Classroom along with today's video. So if you want to see in detail, it's like a 13-minute long video. He takes a cross product. Right, so real fast here, instead of A and B, it could be R and F for radial arm and a force. And maybe we're trying to find the torque. So he sets up the determinant of a matrix. Okay? And he shows you exactly how to find this determinant. You guys, show hands. How many guys have seen this in a math class? How to take the determinant of a 3x3 matrix? Maybe? Yeah, some of you guys? Okay. All right. And again, if you want to see more detail how to do that, I will upload this link later so you can do that if you need to. All right, that's there. Ooh, spool time. All right, so I have, here it is, got the spool. All right. Now, do you guys see an inside radius here and an outside radius here? I said, and I got the string wound around the inside radius. Okay. So what if I set this down on the surface and I pull the string to the right? If I pull the string to the right, which way did this spool turn? Does it go to the right also?
Yeah.
Show of hands. How many guys say this goes to the right if I pull to the right? Let's see if it does. Oh, yeah, sure does. I pull to the right, it goes to the right. Yeah, maybe it goes to the right. Right. All right, what about this? What if I flip this whole thing upside down? Right. Look at that. See how the strings come emerging out the bottom, right, of that smaller radius? I set this down, and I pull this to the right. Now, which way is this going to move? To the right or to the left? Show of hands. How many guys say it moves to the right still? Who says it still moves to the right? Still moves to the right. You guys that? See. Oh, look at that. It still moves to the right. I say, I'll do it again. So I pull the string to the right. It still goes to the right. Huh. Right? No, there's a crazy way you can rig this up to make it go to the left. I'm not going to quite do that. Although there's a YouTube channel, but I think it's Steve Mold does it. He gets it to go the other way eventually, right? But these are some basic ones, right? So why did that still go to the right? Actually, these are the two I just did for you guys, isn't it? Why do both of these go clockwise from our point of view? Right? Now, if you thought this one was going to go the reverse way, you're probably thinking, well, it looks like it's rotating about the center, but it actually isn't. It's actually rotating about this point down here, isn't it? Okay? And this spool had some friction with this table surface, actually, this poster right here. Okay? So, and you need this frictional force to make this work too. So as I pull to the right here, this friction resists that, goes to the left, and oh, look, you get a little torque right here. You can see this R cross F right here. So here's your R, here's your F, R cross F. Right, it'll turn. Right. Now here you get even more torque because there's a much bigger radial arm, R cross F. Here's a little tiny R and F. Right, see, not as much torque, but it does roll off to the right. Okay. Yeah, and there's different ways you can rate that up. All right. Ooh. Okay. Now one of the labs coming up, either this week or next week, depending on how this paces out, is going to be this one. Now, guys, this one's involved, has a lot of little moving parts to it. So I'm going to explain this today, and then you guys can sleep on this tonight, and your brain can process a little bit. So that by the time we eventually do this will make more sense. Okay. So I'm going to one day soon set up this pipe system looks like a T. You guys see this T-looking pipe system? Okay. And there'll be a central axis, and it'll be pretty well free to rotate. Maybe a tiny bit of friction, but pretty well free to rotate. So I can take these arms, give a little tap, and it'll start spinning. Do you guys see that? Right, something like that. Okay. Right. Now, if that's all I had, do you think there would be some inertia, some rotational inertia associated with starting stopping it? Okay. In fact, guys, suppose you had a couple of big old lab weights right here. If I scoop the lab weights closer in, what did I just do to the whole rotational inertia of that system relative to this axis? Got what, bigger or smaller? Smaller. It's easier to start it, it's easier to stop it. What if I scoot them way out here? Now it's hard to get it going, but once it's going, it's also hard to stop it. Right? It's that. Right? Then what we'll do is wrap some string around the central axis, which itself has some radius right here. You see that radius? Right? So wrap some string around, right? And hang a lab weight right here. And then we're gonna let the lab weight go, and it's gonna start to fall. Now, guys, do you think it's gonna accelerate as it's falling? Who thinks this is accelerating as it's falling? Yeah, yeah. Right now, maybe very slowly, but it's speeding up a little bit. It's going a little faster, a little faster. Okay? And we'll say how far does it fall? Call it x, and how much time with a stopwatch t. And if it fell so far and so much time starting from rest, let's see, it fell so far and so much time starting from rest. Let me see, get rid of this one. Could be solved for the linear acceleration. Right? Okay, so this is accelerating down. We can quantify that. Okay, but it's also connected to that central pipe system, which had some radius. So is that going to cause us to speed up spinning with some alpha, some angular acceleration? I label this omega, but really I could label it alpha for angular acceleration. Right? And the connection is right here. You guys remember this one? Right? So here's the center of the pipe system. Might only be like a couple centimeters, right? Something like that, right? Right. So there's some linear acceleration. It has some radius. You can calculate the angular acceleration, right? And once you know the angular acceleration, well, I think we can connect that back to, how about this one right here? Okay. So you know the angular acceleration. And if you know the net torque, which comes from R cross F, something to do with maybe the tension in the string and the radius of that central pipe, right? I bet there's enough information lying around where you can calculate this rotational inertia of that entire pipe system. Is that right? And what we can do too to make it extra fun is to change out these masses with maybe smaller and bigger lab weights, right? And yeah, it should be consistent. It should lead us to one called rotational inertia. All right. Questions on that one? That's good. All right. Let's talk about equilibrium. So last semester, the conditions for equilibrium were pretty much just this right here. The sum of forces goes to zero. And if you introduce a Cartesian system, 2 dimensions, 3 dimensions, along each axis, forces sum to zero. Okay. Now, starting this week, we're going to bring in the final necessary condition, which is that the torque also sums to zero for true equilibrium. Okay. Now, probably a lot of the questions in either honors or AP class are primarily going to be 2-dimensional questions. Okay? But here is what it looks like expanded into 3 dimensions. You get all these conditions pop up. Forces sum to zero, torque sums to zero. Okay? Guys, think about the floor you're sitting on right now. We're all sitting on the second floor of the building, right? Okay? You guys think back 30 some years ago, whenever the engineer designing this building had to consider like every single point in the floor and say, okay, well, what's maybe every one of these conditions right here. Say, okay, well, I'm building this floor with concrete and steel. There's going to be all these students sitting on it with all this lab equipment. Want to make sure it doesn't crumble. It's got to have some strength. Okay? So, but it starts from right here. There's a whole college class I took that was just called statics, and it just starts from this page. Right? So you say, okay, here's your conditions for equilibrium. Right? If you want to build a big building that just sits there for decades, right? And then you can design everything around that. Okay. All right. I have some labs lined up that look well. Okay, here's a seesaw and here's a scaffold. Okay, so one at a time here. Start with the seesaw. Right. So, here, I'll set this up for you guys. I think I may have done this last semester too. I don't know. I forget. I'll do it with you guys right here. Okay. What if I set up my ruler right here, like a seesaw? Okay, that's pretty well balanced. You guys see it? My ruler's balanced. Right. What if I have a couple of lab masses? Right, I'll pick these two right here. Okay. Now, this one says 50 grams and this one says 20 grams. Let's say I don't know one of them. Maybe I don't know this 50 guy. I don't know what that is, right? But I know this is 20. Right? You guys see that? Right. Now, if I set these down, suppose I put them equidistant from the center. Guys, which way is this going to tip? Towards the left or towards the right? Yeah, towards the left. See that? Yes, this one's heavier, right? But what if I take the smaller one and I scoot it closer to this end? Do you think at some point that could actually balance? It could restore balance? Ooh, let's go way out here. That's pretty close. Pretty close. Ooh, it's like all the way. Oh, let's keep this in a little bit even. Well, it's pretty close. Like that. Right. Okay. No, it's really precarious balance, but that's pretty close to balance right there. Guess that balance. Okay. Now again, let's say that I know that this guy's 20 grams, but I don't know what the mass of this is. What I can do is I can apply this equilibrium with torque, and I can say that the torque has to sum to zero. Now, can you guys kind of see through my rulers? Since my rulers are kind of transparent. Do you, okay. Do you guys see how the weight on one side times its radial arm matches the weight on the other side times its radial arm from the pivot point? Yes, okay. All right. So let's do a calculation right here. Let's figure out these radial arms. Now this one's sitting over here at basically 30 centimeters from 15. Guys, what's 30 minus 15? 15. Guess who's a radial arm at 15? Okay. There. Okay, so we got radial arm at 15. There. Okay. And then over here, okay, great. Now it's pretty well balanced right there. Okay. This is 15 to 10. Pretty, yeah, I'm at the other way. Actually, that's a little better. Maybe like 9. Right. Guys, what's 15 minus 9? 6, I think, right? 6. Okay. So here we got 15 centimeters. Here we got 6 centimeters. Okay. And over here I got 20 grams. And I do need a gravity field also. Guys, would this work in space or would it all just kind of float around? Yeah, in space it would just float around. It wouldn't matter where I parked anything. Right. And put some numbers here. I'm going to take this 20 grams times Earth gravity. Well, I'll ignore Earth gravity. It's just going to cancel out on both sides. Okay. Then we'll multiply that by this 15 centimeters. And I'm going to divide by this 6 centimeters. You guys get that? Divide by 6? Okay. That should get me pretty close to this mass. Let's see what the calculator says. Oh, that got it exactly. Great. I promise I did not work that out ahead of time. I just kind of scooted it around so it worked. See, it says 50 right there. Isn't that exactly what this is? 50 grams? Is that? Okay. All right. So what I just did with you guys, here it is in the poster version. So here's my pivot point. Here's this radial arm, this weight, this radial arm, this weight. Okay. And the principle is the torque zeroes out. So if you know everything except for one thing, you can solve for that one thing. And what I solved for was, well, one of the weights. Okay. How about this? Let's get a little bit more abstract with this. Because when I give this to you in lab form, here's an abstract extension. I left off one of the forces. Here's who sees it? Who sees what force I left off this page?
Normal force.
Yeah, the normal force on the pivot. Guys, if this is mg, and this is 3 mg, here, I'll make up some numbers. If what this is 10 newtons, so this is 30 newtons. Is that okay? 10 and 30? How much is this pushing up with?
Around 40.
40. Because there's another condition I didn't write on here, which is the forces have to sum to 0 also. Isn't that true? Okay. So now I picked this as my pivot point because if you sum the torque about this point, well, kind of like if you press on the door hinges of a door, that'll never turn the door. Okay. So this upward force of maybe 40 newtons or whatever doesn't cause any torque about the pivot point itself. Right? But what if you shift reference points? Guys, what if I pick this point right here? Somebody take a guess. What if I sum all the torque about this point right here, including this upward normal force? Guess what the torque sums to? 0. This condition is still true. So here's a weird thing. No, we're getting to more abstract territory. But turns out you can pick this point, this point, this point. You can pick a point off the meter stick over here, and the torque will still sum to 0 mathematically, and you can still maybe solve for an unknown. Okay, get that? All right. Let's do one more poster today. So here's the last poster today. Okay. And actually, it doesn't look too different from one of the midterm questions you guys saw. You guys remember a midterm question where there was maybe like a wood bar here. It was held up by a couple of ropes, and there was a person hanging right at the geometric center. Do you guys remember that? And I think the question was, if the person weighs 500 newtons, what's the tension in each rope? And you guys said what? 250, 250. Because 250, 250 up, 500 down, it's a wash. Right? Then I said, well, what if the person's not hanging at the center? What if you scoot them a little bit to the right, like this picture is? Right? What happens to the tension on the right side? It does increase a little bit. Right? Now, do you think these two upward tensions still add up to the original 500?
Yes.
Yeah, I think this one decreases a little bit. This one increases a little bit. Right. Right. But how much are they exactly? Like put spring scales here. What would the spring scales read? And you cannot solve that with just force alone. You have to also use torque. So here's my two conditions. I have the sum of force goes to zero and the sum of torque goes to zero. You guys see that? Okay. Now sum of force goes to zero. Looks like I have two upward forces. Boom, boom, right there. Right. I have the weight of the bar itself or the beam, and I have the weight of the object here. Right. So that also has to zero out. Right. No, guys, last thing here. Last thing here. Let's look real close to this torque equation. Because remember how from last poster I can pick any point and sum the torque about it, and the torque has to sum to zero, right? But if I have two, suppose I don't know either of these tensions right away. Isn't that like two unknowns, right? Would it be a good idea to pick one of these points as my reference pivot point and sum the torque about? Because if I do that, like if I pick this point right here, doesn't this force at that point cause zero torque about that point? Which is what I did right here. So you can read the music of this equation and realize, oh, this here is the pivot point. Because this force is zero away. The weight of the beam is, well, as long as the weight is uniform, it's L over 2 away. The weight of the object is distance x away. And the other tension is the full length L away. That has to zero out. And now you can solve for the tensions. All right, so that is our pause point today.